Hello, everyone. Welcome to Sleepy Sage's Science Diary. I'm so glad you're here. Maybe you've had a long day, or maybe you're the kind of person who falls asleep not by counting sheep, but by drifting through deep thoughts and the mysteries of the cosmos. Either way, tonight's journey is for you. All you need to do is rest. Let your mind soften, your breath slow, and your body grow light as if gravity itself has eased. Together, we'll explore why the universe feels so perfectly tuned and why time might be an illusion. By the end of this video, I hope you'll have a calmer, deeper understanding of astronomy and our astonishing universe. Is time an illusion? In this video, we dive into why time might be an illusion, exploring the second law of thermodynamics, Newton's absolute time, Einstein's relativity, and the block universe idea. By the end, you'll see how humanity has evolved from merely following nature's rules to decoding the hidden architecture of SpaceTime. Why did Einstein argue that time changes with motion, and why might our everyday sense of time be a deeply rooted illusion? The arrow of time points one way, from past to future. It separates what has happened from what has not. Everything around us displays this forward flow. Waves crash and recede, leaves fall and decay, energy disperses in processes that can't be undone. But why does time seem to move in only one direction? Is that a built-in feature of the cosmos, or a trick of human perception? The answer may hide in small details, buried deep in the structure of reality. Consider a simple example: a box with 100 marbles. At first, you place all the red marbles on one side and all the blue ones on the other, a low entropy, highly ordered state. Then you shake the box. The marbles scatter and mix. After a few shakes, you get a mottled, thoroughly mixed scene, a high entropy state. Putting them neatly back without intervening would take enormous time and effort. In fact, if you keep shaking, the chance that all the red marbles spontaneously regroup on one side is essentially zero. That's entropy in action. Once a system becomes disordered, the odds of it returning to a perfectly ordered state are vanishingly small. Energy, like those marbles, naturally spreads out. In thermodynamics, this means heat flows from hot regions to cold ones and never spontaneously reverses. No matter how advanced your machine, it can't extract energy from a colder place to reheat something without paying a price elsewhere. The second law of thermodynamics ties the direction of time to the growth of entropy. We feel time moving forward because entropy keeps increasing. You can remember a low entropy past those cleanly separated marbles, but you can't remember the future, because that's where the marbles are mixed, and entropy is higher, like the turbulence left behind when steam cools and energy dissipates. Think about your morning coffee. As you pour it, steam rises and the drink cools, its heat diffusing into the surrounding air. The system's entropy goes up, and the process doesn't run in reverse. You never see steam leap back into the cup to make it hot again. To reheat the coffee, you must add new energy, say, in a microwave, which still increases total entropy, because the microwave produces waste heat while doing work. Every time we move energy or perform work, entropy increases somewhere in the universe. Or take an egg. Before you crack it, it's a highly ordered system, yolk and white sealed inside a shell. Once cracked and scrambled, entropy rises. Heating the mixture spreads energy and changes its structure. Reassembling the egg to its pristine, low-entropy state would demand controlling every molecule with absurd precision, practically impossible. This irreversibility gives time its arrow. From a match burning down to ash, From a whole egg to breakfast, rising entropy ensures time runs one way and gives our experience of time a clear direction. Now step into Newton's universe. For Newton, the world runs like a finely tuned machine, and time flows uniformly and independently, unaffected by anything else. Absolute, precise time flows equably, as if by its own nature. Picture time as a metronome's steady tick, constant, unwavering, eternal. Whatever happens in the world, time marches on. To grasp Newton's idea, imagine a fixed cosmic stage on which all events unfold. The stage never changes. Planets, stars, and everything on Earth move like actors, following the clear rules laid out by Newton's laws of motion. Their beauty lies in simplicity and precision. Just as early pendulum clocks divided time into seconds and minutes, Newton's equations let us predict motion with remarkable accuracy. A cannonball arcing through the sky, a planet orbiting the sun, an apple falling from a tree, different scenes, same underlying laws. In Newton's picture, time is absolute, while space is like a three-dimensional grid. Each object occupies a point with length, width, and height. Time draws an invisible line into the future. Objects move through this space-time grid along time's channel, but time itself neither bends nor changes. It keeps ticking forward, second by second. Newton's laws then tell us how objects traverse that grid. In the next sections, we'll see how Einstein bends this rigid stage, merging space and time, changing the tick of the clock with speed and gravity, and why some physicists think all moments coexist in a block universe, where the flow we feel might be more about our minds than about reality itself. Stay tuned. From Newton's clockwork to Einstein's time warp, take a simple throw. When you toss a ball into the air, Newton's second law, force equals mass times acceleration, lets us calculate its peak height and the exact moment it returns to your hand. In those calculations, time is the crucial ingredient, the invisible, rock-solid scaffold of the system. Most importantly, time itself isn't affected by the ball's motion. It advances uniformly and steadily, as if it would march on even if the ball had never been thrown. Newton treated time as an unchanging cosmic backdrop, a view so compelling that it shaped science for centuries. But what if the arrow of time isn't as straightforward as we think? What if our entire picture time's flow and even its direction could be turned upside down? That question cuts deep. It challenges our basic assumptions about causality and the order of the universe. In 1905, working as a young clerk at the Swiss Patent Office, Albert Einstein turned thought experiments into what we now call special relativity. His revolutionary claim, time and space aren't separate, they're woven together into a single fabric space-time. Motion through space actually changes the passage of time. The faster something moves, the slower time runs for it. This flies in the face of classical physics and rewrites our understanding of reality. Enter a famous thought experiment, the twin paradox. Imagine twins, Alice and Bob, born at the same moment and raised side by side. One day, the adventurous Alice boards a starship capable of traveling near the speed of light, while Bob stays on Earth. According to special relativity, time for Alice slows relative to Bob while she's moving at extreme speeds. She accelerates toward a distant star, turns around, and heads home. On Alice's ship, only a few years might tick by. Back on Earth, Bob experiences far more. When they reunite, Bob is noticeably older than Alice. This isn't science fiction, it's a real relativistic effect. Precision atomic clocks on airplanes and on the ground have confirmed time dilation exactly as Einstein predicted. General relativity goes further. Gravity itself bends spacetime. Near a massive object, say, the edge of a black hole, time stretches and warps. The stronger the gravitational field, the more slowly time passes. This gravitational time dilation has been measured with exquisitely precise clocks separated by altitude on Earth and in flight, and the effect becomes extreme near a black hole's event horizon. Alice isn't satisfied with one brush with the strange. After witnessing the weirdness of high-speed travel, she sets her sights on time's behavior near a black hole, where gravity pushes spacetime to its limits. Her destination, Sagittarius A*, the supermassive black hole at the Milky Way's center, about 4 million times the mass of our Sunday. A journey like this would take unimaginable spans by ordinary means, but aboard a near-light-speed craft, Alice's own clock might record only weeks. As she approaches the galactic center, she sees the black hole's blazing accretion disk matter whipping around at incredible speed and emitting fierce radiation surrounded by a darkness from which not even light can escape. Closer and closer to the event horizon, gravitational time dilation intensifies. The black hole ceases to be a mere equation in a textbook and becomes a tangible, merciless curvature of space-time itself. So is time fixed and universal or elastic and personal? Newton's metronome or Einstein's rubber sheet? As we follow Alice and Bob, the answer becomes clear. The flow of time depends on how and where you move through the universe. At the edge of a black hole, what happens to time? As Alice's starship sinks deeper into the black hole's gravitational well, time dilation reaches its extreme. But what exactly happens at the event horizon? To answer that, we have to lean on the mathematics of general relativity. Near the horizon, space-time curvature becomes violent, and the rate at which time passes changes dramatically. From the viewpoint of a distant observer, anything falling toward a black hole appears to slow down, its clock nearly stopping as it approaches the horizon. That doesn't mean the infalling object's own time has halted. In its proper frame, time passes normally. To an outside observer, however, the object seems frozen at the brink, never quite crossing the horizon. This strange split is born from the relativity of simultaneity. As Einstein showed, the notion of now isn't absolute, but depends on your frame of reference. In the extreme environment around a black hole, that relativity becomes impossible to ignore. There's another twist: gravitational redshift. Because of the black hole's intense gravity, light from the infalling object is stretched to longer wavelengths. As it nears the horizon, its light redshifts so severely that it slips beyond detectability. To the faraway observer, the object fades from view not because it vanishes, but because its signals are dragged into invisibility by warped spacetime. What about the traveler's own experience? For someone who actually crosses the event horizon, there's no flashing sign, no sudden boundary. They drift through the horizon without noticing anything locally special and continue to experience time as usual. But as they approach the black hole's central singularity, where space-time curvature tends toward infinity, our ordinary notions of direction and duration break down. Here, general relativity itself ceases to be a reliable guide. To understand this regime, we need quantum physics and ultimately a theory of quantum gravity. That need leads to a deeper puzzle. If things seem to disappear inside a black hole, what happens to all the information they carry, their mass, energy, and every microscopic detail? Stephen Hawking's calculations showed that black holes radiate and gradually lose mass, a process now called Hawking radiation. If a black hole can evaporate away entirely, where does the information go? Quantum theory insists that information is never truly destroyed. Hawking's results seem to imply the opposite, triggering the famous information paradox. One proposed answer is the holographic principle. Perhaps the information that falls in isn't lost, but is somehow encoded on the event horizon itself. In this view, the horizon behaves like a two-dimensional surface capable of recording all the three-dimensional data of whatever enters. It's a speculative but powerful idea that resonates with the black hole's peculiar mathematics. Push that idea further and you get a dizzying possibility. Maybe our three-dimensional universe is itself a projection from a more fundamental two-dimensional reality. If so, the flow of time we feel could be a complex projection too, not a simple river from past to future, but part of a timeless structure in which all moments coexist. That brings us to the block universe. Picture a loaf of bread, each slice a specific moment. A birthday, a first day of school, a test you aced, a first love, even your final breath. You stand on one slice called now, but the other slices exist just as surely. They don't have to be recreated, they're simply there. Now imagine not just one loaf, but a whole bakery, each loaf tracing the history of a person, a planet, a particle. These loaves are not isolated. They overlap and touch. The instant you meet someone for the first time, the moment a world event ripples through millions of lives. Those intersections are the nodes where different threads of the cosmos interweave. In a block universe picture, past, present, and future all inhabit a single four-dimensional space-time block. Time doesn't flow from one moment to the next. Instead, every moment simply is, like the pages of a book whose story is already written from beginning to end. It's a startling, even unsettling view. But it follows naturally from relativity's lesson that now is not universal, and it forces us to rethink causality, free will, and what we mean by reality itself. If time is just one dimension of space-time, then what we call choices might simply be a journey along a path already laid out. From within the block universe, time feels like it flows. Moments seem to unfold one after another, and our choices feel vital. But at a deeper level, every instant birth and death, choices and chances may be nothing more than coordinates coexisting inside space-time. And that still isn't the end of the story. Push the idea further. What if the entire loaf, our sense that space-time is continuous, is itself an illusion? What if before and after don't exist, not because all moments coexist, but because sequence and progress never existed to begin with? Imagine that what we call reality, every timestamp, every memory, every tick of the clock, doesn't merely coexist with other moments, but at its core is nothing like what we think it is. This radical possibility challenges our most basic intuitions about time and existence and opens a new way to think about what's real. So what is time? Perhaps it doesn't flow at all. Perhaps every moment simply is, fixed and unchanging. We feel a flow only because we can experience one slice at a time, as if we're trapped inside a still frame, unable to see the wider panorama. In this view, the universe isn't a place that changes as time passes. Time is part of the structure itself. All times are locked into a four-dimensional block where past, present, and future are equally real. Your life, birth to death, already exists in full within that structure, eternal and unaltered. But if everything is already written, what becomes of free will and change? Looking ahead, it's reasonable to expect new insights that reshape this debate. As technology and theoretical physics advance, we may eventually build a framework that explains what time truly is, whether it exists independently, is merely one dimension of the cosmos, or belongs to an entirely different category. Until then, time's ambiguity reminds us of the limits of our understanding. Instead of endless argument over its ultimate nature, we can treat time, whatever it is, as a call to live meaningfully. Whether time is real or an illusion, it is central to human experience. By focusing on the present, shaping our relationships, actions, and identity, and attending to what we can actually influence, we can live fully no matter what time turns out to be.